Today we're diving into something pretty critical in modern crypto, making sure the foundations, these cryptographic commitments, are actually solid.
Right, specifically in the context of these advanced proof systems, SNARKs.
Exactly. You, our listener, told us you want to grasp these complex topics quickly, get those light bulb moments. So we're looking at a really cutting-edge problem and some potential solutions. Our mission today is really to understand why ensuring the integrity of these pre-computed values is so crucial for things like SNARKs.
And also how Frost might be, a much more efficient fix than older methods like secure multi-party computation or MPC.
Precisely. So let's dig in.
Okay, let's start right there. Why is the integrity of these commitments in SNARKs? Why is that such a big deal?
Well, like the seminar presenter explained, SNARKs, systems like G16, or their own one, Tokamak, they get their efficiency from relying on these pre-processed commitments to the circuit polynomials.
Things like the CRS, the common reference string.
Yeah, the CRS in G16,
Right.
or you might have gate selectors, permutation polynomials, and other systems like PL and K. They're the essential groundwork. They make the whole thing work succinctly.
Gotcha. Like the prepped ingredients for a complex recipe. And currently, these are either set up by the verifier themselves or they're outsourced.
Exactly. And that outsourcing, that's where the problem lies.
Yeah.
How do you know, like really know, that those outsourced commitments are correct, that they haven't been messed with?
Uh-huh. How do you guarantee integrity?
That's the central question the seminar was tackling.
Makes total sense. If those foundations are dodgy, the whole proof system could just, fall apart. So what are the existing solutions and what's wrong with them?
Okay, so one approach mentioned is secure multi-party computation, MPC.
Right.
The idea there is you get multiple parties working together to generate these commitments. They gave an example of a two-phase MPC for generating the G18 CRS.
So it's sort of a cryptographic group project. Everyone ships in a secret piece, and if just one person is honest, the result is trustworthy.
That's a pretty good analogy, yeah. The security rests on that assumption, at least one honest participant. But MPC has drawbacks, especially if you need to check integrity often.
Okay, like what are the hurdles?
Well, the seminar really hit this point hard.
Mm-hmm.
MPC involves a lot of communication.
Okay.
Back and forth between all the parties. And the provers, the participants, it's computationally expensive for them. It costs a lot to take part.
Ah, so it's slow and costly.
And the big one, maybe, is the time commitment. A single MPC ceremony can take weeks, sometimes months, just for one instance.
Wow, months. Okay, so definitely not practical for frequent checks.
Exactly. It's secure, but cumbersome.
So if MPC isn't great for regular use, what's the alternative? This is where threshold signatures like Frost come in.
Precisely. Threshold signature schemes are presented as a more, let's say, lightweight alternative for this integrity problem.
Okay, how do they work, basically?
So imagine you've outsourced a polynomial commitment. Let's call it AX. Now you have a group, maybe N signers. Each one independently checks if AX is correct, and if it is, they sign it.
Like a group of notaries, each putting their stamp on it?
Kinda, yeah. And the clever part is all those individual signatures can be combined, aggregated, into one single compact signature.
Oh, neat.
And then anyone can check the integrity just by verifying this one aggregated signature and maybe a small extra proof. The only condition is that enough of the original signers, a certain threshold, T out of N, were honest.
So instead of a massive MPC ceremony each time, you rely on this group signature, assuming a decent number of the signers are trustworthy.
That's the idea. It's potentially much more efficient than these infrequent, massive MPC setups.
Okay. Now, the seminar mentioned we should understand the basics of Schnorr signatures first to really get Frost. Can we do a quick rundown?
Sure. The basic Schnorr signature is just two parties. Peggy, the prover, and Victor, the verifier.
Okay.
They agree on a setup, a cryptographic group, a generator, G. Peggy picks the secret keys and calculates her public key, Y, which is just G to the power of S. She keeps S totally secret.
Right, secret keys, public key, Y.
Then, to sign a message M, Peggy does a few things. First, she picks a random number, sometimes called a nonce or a mixer. It's temporary. She computes a commitment R, which is G to the power of R. Then she calculates a challenge, C, this is a hash of R, her public key Y, and the message M.
Hashing all this together.
Yep. And finally, she computes a proof Z, which is R plus C times her secret key. She sends R, C, and Z over to Victor.
All right, so Victor gets R, C, and Z. He knows G, Y, and M. How does he check it?
Victor first recalculates the challenge, C himself. using the R, Y, and M he has. Hashes them the same way Peggy did.
Okay.
Then he does the main check. Does G raised to the power of Z equal R multiplied by Y raised to the power of C? If that equation holds true, the signature is valid.
It's like a mathematical puzzle that only works if Peggy used her correct secret keys.
Exactly, and it relies on the difficulty of the discrete logarithm problem. It's hard to find a Z's just from Y.
The seminar mentioned completeness, soundness, zero knowledge briefly. What did those mean here?
Right, completeness just means an honest security. Peggy's signature will always verify. Soundness means if Victor accepts, Peggy almost certainly does know the secret keys. And zero knowledge means Victor learns nothing about S itself, just that Peggy knows it. That random mixer R is key here. It kind of hides S within the proof Z.
Got it. The random R keeps the secret safe. So that's single signer Schnorr. How did they make this work for multiple signers back in 2001?
They use the linearity, the sort of additive properties, the math involved. For N signers, they first run something called verifiable secret sharing. VSS.
VSS.
Yeah, think of it as a way to securely split the main secret keys into shares, one for each signer, so no one knows the whole thing. This process also generates a single global public key Y that everyone agrees on.
So shared public key, but individual secret share.
Exactly. Then to sign a message M, each signer I generates their own random mixer I and computes their commitment I.
Okay.
An aggregator collects all the I's and combines them into one aggregate commitment R. The challenge C is calculated using this aggregate R, the global public key Y, and the message M.
Similar to before, but with the combined R.
Right. Then each signer calculates a partial proof C using their secret share and their read. The aggregator sums up all these C's into the final proof Z.
And verification.
Verification by Victor looks pretty much the same as a single signer case, using the aggregate R, Z, and the global Y.
Okay, so it seems like a neat extension. But the seminar stressed that Frost was needed because this 2001 scheme had a vulnerability.
Yes, a significant one. It turned out to be vulnerable to chosen message attacks, specifically using something called Wagner's algorithm.
Yeah.
The 2019 paper really highlighted this.
Chosen message attacks. What does that mean here?
It means an attacker could potentially trick the group of honest signers into signing several different messages the attacker chose.
Okay.
And the flaw was, if the attacker chose those messages carefully, satisfying certain mathematical conditions, they could combine the resulting legitimate signatures to forge a new signature.
Whoa! Forge a signature on a message the group never actually agreed to sign.
Exactly, by mixing and matching parts of the real signatures. And Wagner's algorithm gave them a practical way to find a target message that would allow this forgery.
That sounds like a pretty major security hole.
It absolutely is. It undermines the whole point of the signature scheme.
Yeah.
And that's the core motivation for Frost to fix this vulnerability.
Right. So what does Frost do differently? What are the key upgrades?
The seminar highlighted two main things. First, big difference. Each signer uses two random mixers, not just one. Let's call them Ty and I.
Two random numbers per signer per signature. Okay.
Second, Frost uses the hash function twice in the signing process, where the older scheme used it only once.
Double hashing.
Yep. These two changes, two mixers and double hashing, are the core defenses against Wagner's attack. There's also a detail about an aggregator selecting subsets of participants, but that's mainly for dealing with potentially dishonest aggregators, not directly against Wagner's attack itself.
Okay, two mixers, double hashing. Let's get into the signing process in Frost a bit more. How does it change step by step?
So each signer picks their two random mixers, Ty and I. They publish commitments related to both of these.
Commitments to both mixers go public first.
Right. Then the aggregate commitment R in Frost. It's not just a simple sum like before. It's a more complex combination involving these commitments. And crucially, it involves a hash function being applied inside the exponent in the group operation.
Whoa, okay. So the math gets fancier right from the start, inside the exponent.
Yeah, without getting lost in the exact formula, the key is that the way R is built is significantly more intricate.
And the final signature itself, S, I think they called it.
The signatures in Frost is also more complex. It involves hashing multiple things together, including the aggregate commitment R and the message M. But importantly, it involves hashing the output of other hashes. That's the double hashing aspect.
Okay, so complexity added in constructing R and complexity added in constructing the final signature S through double hashing. How does that stop Wagner's attack?
Well, the presenter explained it like this. In the old scheme, the attacker is trying to solve an equation, basically finding a target message that makes the forged signature parts fit together correctly.
Right.
The weakness was an imbalance. The set of possible inputs that could satisfy one side of the equation was much smaller than the set for the other side. Think of it like having fewer keys for one type of lock. Wagner's algorithm could exploit this imbalance.
Like a generalized birthday attack kind of thing, finding collisions.
Exactly. Frost, with its double hashing and more complex structure, essentially makes the number of possible inputs, the pre-image sets, roughly the same size on both sides of the equivalent equation the attacker would need to solve.
It balances things out.
Precisely. It makes finding that magic combination, finding a message that allows a forgery, computationally infeasible. It becomes incredibly hard, effectively thwarting Wagner's attack.
So the added complexity directly counters the specific mathematical trick the attack relied on. That makes sense. Now, you mentioned the presenter had an open question about Frost.
Yes, this was quite interesting. They were still pondering why exactly Frost needs 2 random mixers, Ti and E, per signer. Why not just one? They mentioned thinking, well, maybe you could just set one of them to 0 and it would still be secure. But apparently, the original Frost paper doesn't give a crystal clear knockdown argument for why 2 are strictly necessary.
So even in these advanced schemes, there are still some design choices that aren't perfectly understood or justified.
It seems so, or at least the justification wasn't immediately obvious from the primary source they consulted. It suggests there might still be nuances to explore there.
Fascinating. Okay, let's talk about the Q&A session from the seminar. Those often bring out useful details. What came up?
Yeah, some good points were raised. One question was about efficiency. Is it repetitive for every signer to check the integrity of that initial commitment A? Seems like duplicated effort.
Good question.
The answer was basically, well, yes, it might seem that way. But right now, there isn't a known efficient way to check that integrity without something like running a Snark verifier. But using a Snark to verify the setup for another Snark, that's circular.
Right, you can't use the thing to secure itself before it's secure. Catch-22.
Exactly. So for now, individual checks seem necessary, even if maybe not optimally efficient.
What else?
Key distribution came up. Is something like DKG, distributed key generation, or VSS needed?
To set up the shares initially.
Yeah. And the answer was a definite yes. You absolutely need a secure mechanism like DKG or VSS to establish those secret shares in the global public key properly. They briefly mention VSS often has a designated dealer, while DKG is more decentralized. Everyone contributes.
Crucial setup step then. Did the mystery of the 2 mixers come up again in the Q&A?
It did. Someone offered a potential explanation. The idea was maybe using 2 mixers, sort of structured like the R plus CS part of Schnorr, but done effectively twice, just makes forgery fundamentally harder for an attacker, adding layers of algebraic complexity.
Layering the security.
Another suggestion was about binding commitments more tightly, preventing an attacker from choosing certain values adaptively after seeing others. So, likely security reasons, even if the exact proof wasn't pinpointed in the discussion.
Makes sense. It feels like an extra safeguard against clever attacks. Anything else significant from the Q&A?
Yes. Confirmation that Frost's security proof is in the random oracle model and relies on an assumption called the linear random function, or BRF assumption.
Okay, standard cryptographic assumptions.
And a really critical practical point.
Okay.
Never, ever reuse the random mixers, Ti and I, across different signing sessions. Doing that could leak your secret key share.
Huge security no-no, fresh randomness every time.
Absolutely. And they also confirmed that the 2 mixers, often called D and I in the papers, are generated independently, possibly from different distributions, for each signature by the same user.
Got it. Independent, fresh randomness for both mixers every single time. That Q&A really added some practical depth.
It really did. It underscored that even with advanced schemes like Frost, the details of implementation and key management are absolutely vital.
Okay, let's try and wrap this up for the listener. What are the key takeaways from this deep dive on Snark integrity and Frost?
I think the main thing is understanding why integrity of these pre-computed values is so fundamental for Snark security. You can't build a secure house on shaky foundations.
Right.
And while MPC is a way to build those foundations securely, it's often too slow and costly for frequent checks or updates.
Impractical for dynamic situations.
Exactly. And that's where Frost comes in as a more efficient, more agile alternative. It's a threshold signature scheme designed specifically to tackle vulnerabilities found in older schemes, like the Wagner's algorithm attack.
Using those key innovations, double hashing and 2 random mixers per signer.
Precisely. Even with that lingering question about why exactly 2 mixers are needed, The overall approach offers a significant security improvement for ensuring integrity in a more practical way than just relying on massive MPC ceremonies all the time.
So it's about having the right tool for the job. Maybe MPC for the initial big setup, and something like Frost for ongoing integrity checks or for components that change more often.
That seemed to be the implication, yes. A more nuanced approach depending on the specific need.
This has been incredibly insightful. It's amazing to see the evolution of these cryptographic techniques, constantly trying to plug holes and improve efficiency.
It really is. And it leaves us with a thought, doesn't it, for you, the listener? As we rely more and more on these complex systems, often involving outsourced computation, how will that fundamental trade-off between efficiency and security continue to evolve?
Yeah, what comes next?
What other clever ideas or techniques might emerge to keep guaranteeing integrity as these proof systems get embedded in, well, everything from finance to identity? It's definitely a space to keep watching.